Hi there, this is Maria, and today we'll learn about special right triangles, 45, 45, 90-degree triangles. This is under the Geometry Common Core State Standard for Similarity, Right Triangles, and Trigonometry, which states that using trigonometric ratios and Pythagorean theorem, we'll be able to solve right triangles in applied problems. For today's objectives, we will use a square to explore and discover the shortcut methods in determining the relationships among sides of a 45-45 90-degree triangles. And using the same shortcut method, we will be able to solve for the missing side of a 45-45 90-degree triangles. Okay, now let's begin with a square with all sides equal and with all four 90-degree angle. If we will draw our diagonal, thus forming two right triangles with both 45-45 acute angles. And then if we're going to solve for the diagonal, we are also solving for the hypotenuse. So we have to use our Pythagorean theorem, a squared plus b squared equals c squared. Say for example, the legs or the sides of our square are both 2 units long. Substituting it to the formula will give us 2 squared plus 2 squared equals c squared. And simplifying, we'll get 4 plus 4 equals c squared. It will give us 8. But taking the square root of a number that is not a perfect square, we have to look for a perfect square factor of 8, which is going to be 4 times 2. And taking the square root of 4 will lead us to 2, and leaving the other number that is not a perfect square under the radical. So when the legs are both 2, our hypotenuse or the diagonal would be 2 square root of 2. Now let's have a square whose side lengths are 4 units long. If we are to find for the hypotenuse or our diagonal, we will be using the same formula, a squared plus b squared equals c squared. Now replacing the values of a and b will lead us to 4 squared plus 4 squared equals c squared. And simplifying, we'll get 16 plus 16 is going to be 32 equals our c squared. Taking again the square root of a non-perfect square radical, we have to find a perfect square factor of 32, which is 16 times 2. And taking the radical out would be 4 radical 2 as our diagonal when the side lengths are 4 units long. So, have you observed any pattern yet with our hypotenuse length? Let's try it one more time. This time with a square having side lengths of 6 units long. Using the Pythagorean again, we will have 6 squared plus 6 squared equals c squared, giving us 36 plus 36 would be 72. Taking the square root of 72 will lead us to its perfect square factor of 36 times 2. Now, taking the square root of 36 will give us 6 radical 2 as our hypotenuse when the legs are 6 units long. Okay, let's have now a recap of what we have so far. On the first 45-45 90-degree triangle, we use side lengths of 2, and we are able to find the hypotenuse to be 2 square root of 2. Then on the second one, we have side lengths of 4, and our hypotenuse turned out to be 4 radical 2. And on the last one, we use side lengths of 6, and the hypotenuse we have is 6 square root of 2. So based on this observation, the hypotenuse is always the product of the leg and square root of 2. We will now try to show this shortcut rule using a formula on the next slide. Now let's try to show a general rule in solving for the hypotenuse of any 45-45 90-degree triangle. Let's use x as our legs, and using the Pythagorean, we will have x squared plus x squared equals c squared. Adding these like terms, we will have 2x squared equals our c squared, and taking the square root of both sides will lead us to our hypotenuse when legs are x as x times square root of 2. So, we have generalized that for any special isosceles right triangle, the hypotenuse is the square root of 2 times the leg. Now let's try to apply what we learned about the special right triangle. Try to solve the next two questions applying the shortcut rule that we have just discovered. Good luck! Now for more practice, click on the link to watch the video tutorial. Thank you so much for watching.